I'd like to. You guys can see it. Hey, I still haven't finished.
We have 1 night.
We just went to his office hours, so he could school us something else.
You what?
He taught us linear algebra. Because we don't forget.
He explained to us what the derivative was. It was really fun.
Starting from
Yeah, I think you're right, Kelly. You can't just with that S. You can't just do this. So the way we do. But I don't think you. Yeah, we're supposed to go like this with the trace, and then this becomes tractable because then we can move this in and switch it.
Yeah, I'm curious about it.
But this is wrong.
Right.
Good call.
Today I realized I don't know how to do this full or
Same. I guess I took multi such a long time ago, and yeah. And I'm just gonna. What is it? Just like keep going further.
Don't forget your multiplication.
It's pretty fun. I remember memorizing that. That's kind of felt proud of myself.
Do you want to take this outside? This one will
Nice. Like cheating. Yeah, it's good. It's gonna take Just portion of it. ABC, C, DCA. That's where that's what. No, it's the full quantity of the trace. That's why I distribute.
Okay, good afternoon, everyone. I think we should start. So before we come back to the class topic, I want to say something. I'll clarify a few points first. The administration of our department told me the office hours should not be held in the 3115, and I'm kind of confused because they told me at the beginning they changed to some room, and now they changed the decision again. But anyway, I'll update the room for the office hour later, and website, in the course website, in the syllabus, and also I will make an announcement in the Canvas, so that when we want to come to the office hour, we won't enter the wrong room. And second thing is the usage of office hour. So we really want to help you address problems like in homeworks, in projects, or in understanding the course content. So that's why we give the office hour every weekday. So from Monday, Tuesday, Wednesday, Thursday, Friday, every day we have an office hour. And unless there's some like special circumstances, for example, one of our TMs recently this week has to travel outside. But in most of the time we are available. And also, if you allow to post questions on Canvas, that's good. But if you are available, please come to the office hour, because face-to-face communication is the most effective way. But here, I emphasize that start to do your homework early, and start to ask a question early, right? And don't try to seek for help at 1 minute before the deadline. At that time, there are too many students queuing, looking for the help, right? Seeking for the help. We cannot guarantee that. I mean, the time allocated on you is satisfactory to you, or is enough. And actually, we found that this is always the case. That I keep encouraging my students to come to the office early, but office hour early, but most of the time our office hour is just empty. But anyway, if you want to get more help, and I think a more effective or efficient way is to come to the office hour and try to come early. Like don't you try to like come to, I mean, together come to the office. Like I cannot address your question like for 1 hour because I have to allocate time for your fellow students as well. Any question? And third one, third thing I want to mention is the homework 0. So for the request of many students, I didn't realize that the homework problem sounds not that obvious to quite a few. So I can extend the homework deadline to next Monday. Does it make sense? Yeah, and but be careful. We will release the second homework before the end of this week. So again, please start homework 2 early as well. And don't worry. And we will release the homework answer. We will release the homework solutions after we collect our submissions and give the grades. So if you still have any problems in understanding homework solutions, or feel confusing those problems, feel free to come to the office hour and I'll try to help you. But I have to emphasize that those problems are only 1 mark problems. Those are only used to test your foundations in basic calculus, statistics, and linear algebra. So if you feel like if you are irritated by those problems, if you're really uncomfortable about those problems, come to me. We need a discussion because our class is not some entry level class; it's graduate level class. So we by default assume at least you are not afraid of them. You are not sick of those basic concepts. Otherwise, it might be troublesome to take the class. Again, I mean, I repeat this for 1,000 times. I really want everyone to learn something useful and meaningful from the class. I don't want you to suffer from this class. So again, like if you just feel like I know medicine come to me just I never used matrix derivatives before, but I feel comfortable about those random variables, expectation, those kind of things. That's fine. Doesn't matter. But you feel like sick of the question like prove probability of unions less than or equal to summation of each event, probability of each events. If you're worried about those kind of problems, we need to work our way out. So any concerns about homework problems? Is everybody happy with the extension? Okay, great. So let us continue with the conjugate priors. So at the end of last lecture, we have introduced the concept about the conjugate priors. So what is conjugate prior? Any impression? So first, the conjugate priors is not some concept for one distribution. It's actually about the relationship between a distribution and a likelihood. So you cannot say, okay, a Gaussian distribution is a conjugate or a distribution. It's meaningless. You should claim that it conjugates to what?
Is it the relationship between the likelihood and the posterior, or is it just any two?
Well, if you want to define the conjugate prior, you have to state the relationship between the prior, likelihood, and posterior, right? Because everything comes from the base rule, right? Yeah, but when we refer to conjugate prior, you need to know this actually represents a relationship between the prior and likelihood. So what is conjugate prior? Basically, if you can use base rule giving a prior and likelihood, you can use base rule to calculate the the posterior distribution, and turns out that the posterior distribution has exactly the same functional form as the prior. Then this is called a conjugate prior to this likelihood. So, so let us read this definition again. Given a prior distribution and a likelihood function. Remember, this is something about prior and likelihood. If we'll apply the base rule here, right, and the corresponding posterior distribution has the same functional form as the prior distribution, then we call the prior distribution is conjugate to the likelihood. So we mentioned the first example, that is about the Bernoulli likelihood, right? So the conclusion is that beta prior is conjugate to Bernoulli likelihood. And we can verify it, right? So first, what is beta prior? Any question about beta prior? Well, beta prior is kind of a distribution that samples probabilities. A probability is between 0 and 1. Right? So beta prior ensures that each sample is between 0 and 1. So we can use that to represent, say, when you toss a coin, the chance that you see ahead. Right? You can use as to describe the chance that you win the gambling. So basically, when you generate sample from a beta prior distribution, you end up with a positive non-negative value between 0 and 1. And then we can use this non-negative value as the parameter to do some random experiments, say toss a coin or bet, right? So this is the density for the beta prior. So the beta prior for this parameter mu, right, for this variable mu, is determined by two parameters, a and b. Both a and b should be positive. So this is a form of that. So here I just ignore the normalization constant. Just keep the terms which contain mu, right? They are random variables. So it is mu to the power of a minus 1 multiplying with 1 minus mu to the power of b minus 1. Right? So this is a beta prior, the form of beta prior. And now suppose I use beta prior to generate a probability mu. Remember, it's between 0 and 1. And now I use this probability to sample a binary observation, which is referred to as a Bernoulli experiment, right? Bernoulli experiment is just toss a coin and say whether you get ahead or not. Right? So then I made an observation x. So x is either 1 or 0, right? So the likelihood of this Bernoulli distribution is simply mu to the power of x multiplying with 1 minus mu to the power of 1 minus x, right? So x is either 1 or 0. So x is 1, then the Bernoulli likelihood is mu. If x is 0, the Bernoulli likelihood is 1 minus mu. So now we have prior and likelihood, right? And now, given the observation x, I want to compute the posterior distribution of mu, the posterior distribution of the probability mu. So how do we do that? We know the posterior distribution is proportional to the prior multiplying with likelihood, right? So the prior has this form, beta prior has this form, and the likelihood has this form. So when we multiply them together, we just need to merge the exponent, right? We just add up the exponent. We share the same basis. So mu, the exponent for mu will be a plus x minus 1, and the exponent for 1 minus mu will be b plus 1 minus x minus 1, right? So now we look at the form of this posterior. Although we do not know the normalization constant, but we know that this form is exactly the same as the beta distribution form, right? Except to the detailed parameters. Right? And then we can conclude that the posterior of mu given x is another beta distribution, and parameterized by a plus x, b plus 1 minus x. Right? Then we can claim beta prior is conjugate to the Bernoulli likelihood. Why? Because the posterior has the same form as the prior form, except you change the parameters. Any question? This is just a review of the last 5 minutes of the last lecture. And x is either 1 or 0, right? So this here is one example. So if I choose a and b equals to 2, this is beta prior. So if you make a and b to be equal, that means in the prior beliefs, you believe the chance, the probability mu to be less than 0.5 or bigger than 0.5 has equal chance. But if you observe a binary variable to be 1, so I use the sample mu to make a random experiment, I observe 1. Then my likelihood becomes a function, a linear function mu. Right? You just check it, right? Because the Bernoulli likelihood is mu to the x, 1 minus mu to the 1 minus x. Right? So x is 1, now 1 minus 1 now becomes 0, so it is mu. The likelihood function in terms of mu will be a line. So then, if you multiply the prior and the likelihood, you end up with posterior, because this is a conjugate prior. So we know the posterior must be a beta distribution as well, and just follow the equation result we have just derived. We know that the posterior will be a mu 3, 2. The beta prior, or the beta distribution, the two parameters will be 3 and 2. And if we draw the density for this posterior distribution, you will see it bows toward 1. So it means in my posterior distribution, I believe this probability is more likely to be bigger than 0.5. Why?
Because we observe.
Yeah, because we have observed 1, right? So if we don't have any observations, well, I just assume, okay, they are equal likely to be bigger than 0.5 or less than 0.5. But now I have observed 1, right? Of course, I will assume that the mu should be more likely to be bigger than 0.5. Otherwise, why should I observe 1 rather than 0? Right? So you can see how the posterior distribution can adjust your beliefs through the observations or through data. So let us look at a more generalized example. So then we'll switch to the pad. I want to write something. So let us consider we have a categorical distribution. So I have a categorical distribution, and it's known that the Dirichlet distribution is conjugate to the categorical distribution. Still have an impression? You still have an impression for the Dirichlet distribution? So what is this the Dirichlet distribution? What is the property of the samples generated by the Dirichlet distribution? The sample is a probability vector. Right? So for any vector, so if it's k-dimensional Dirichlet distribution, that means any sample is a k-dimensional vector. Right? So I have say mu is follows the Dirichlet distribution, then mu should have k elements, right? And we know that each element is between 0 and 1, and also the summation of these elements are 1. So it's a probability vector. Just like if I want to use categorical distribution to generate some sample, right? But I know the categorical distribution is determined by a probability vector. Each element in that probability vector determines the chance that your categorical variable taking that particular category. So the sample of Dirichlet distribution is such a probability vector. So now, a stronger conclusion is that Dirichlet distribution not only can offer you a probability vector with which you can sample the categorical variables, but also it is conjugate to the categorical distribution. To verify this, we can first review what is the density function for Dirichlet distribution. So first, I explicitly write down the normalization term here because we'll revisit this term when we study the topic model. You need to know what's this for. So basically, in the numerator, it's a gamma function of the summation over all the alpha 1 to alpha k. So the Dirichlet distribution is determined by a positive vector alpha. So alpha has the same dimension as mu. Has the same dimension mu, and we should ensure that all the elements of alpha are positive. And now, in the density function, alpha 0 here is just the summation of all the elements in alpha. So you have a numerator to be the gamma function over the summation of all the alpha values, and the denominator to be the product of the gamma function over each element in alpha. So remember gamma function. What is gamma function? Yeah, it's a continuous version of factorial. Continuous version of factorial. And then the terms that relate to our random variable mu is this production. Each term is mu k to the power of alpha k minus 1. Okay. So this is the density for the Dirichlet distribution. So now suppose I use this Dirichlet distribution to generate one sample of mu, a particular probability vector, right? And now I use this probability vector to sample a categorical random variable. So categorical random variable is denoted by a one-hot encoding vector, right? So it is also x here is also a k-dimensional vector. The difference is that only one element will be 1, others are 0, right? So it could be 1, 0, 0, 0, blah, blah, blah. And then the likelihood of this categorical distribution would be the product of each mu k to the power of xk, right? Because there will be only one element in x to be 1. So this will equal to the particular probability that x taking the corresponding category, right? Now we can try to calculate posterior distribution. I have used the prior. I have used the Dirichlet distribution to generate a sample mu probability vector, and based on that, I conduct random experiments. I observe the categorical variable, and now doing reversely, I can calculate the posterior distribution of the mu. Right? So to do that, we just multiply the prior with the likelihood. Right? So now we can first forget about the normalization constant and just merge the terms regarding mu, right? Because we only care about mu. We only care about the posterior distribution with mu, so we can just first work out the terms that relate to mu. Right? It turns out that we simply merge those terms which share the same basis, right? And just as the exponent, we still get a product over k categories, and each term is mu k to the power of alpha k plus xk minus 1. Right? But remember, among all those different xk's, there is only one element to be 1. Right? All the others are just 0. Now the question is that, what is this posterior distribution?
Is it a theorem?
Yeah, it's a derivative again, right? Because it has exactly the same form here, right? It's mu k to the power of something, right? -1. So the only difference is the particular value of those exponent. Right? So then we can conclude that the posterior distribution of this probability vector mu given the observation observed categorical variable x is another derivative distribution and parameterized by our observed variable plus the prior parameters of. So it's actually a generalized version of the beta distribution of beta posterior.
So what happens to the normalization of the gamma function?
Yeah, that's a very good question. Given this part, you should be able to immediately get the normalization constant, right? You just substitute alpha 0, alpha 1, alpha k to alpha k plus x. Right? You immediately get it. And then the posterior has the same functional form as the prior, so the derivative distribution is conjugated to the categorical likelihood. Okay? So for continuous random variables, you know that gamma prior is conjugated to Gaussian likelihood. But to be reverse, you should say if I put the prior over the inverse variance or precision of your Gaussian distribution, then gamma prior is conjugated to that. So what is precision? Inverse of the variance. So next time we'll find this term precision, don't feel strange. It just means inverse of the variance. So suppose I use gamma distribution to sample lambda. So lambda is an instance of this gamma distribution. So remember, gamma distribution is determined by these two positive parameters as well, and this is a form of the gamma distribution. So for the terms that only relate to lambda, it is lambda to the power of a minus 1 times exponential to the power of minus b lambda. And now, if we use lambda as the precision of a Gaussian distribution, and to sample a Gaussian random variable, we can write down this density, right? So it's still it's also an exponential form. Now we want to calculate the posterior distribution of lambda, the posterior distribution of this precision. How can we do that? Again, it's quite mechanical. You just multiply the prior with the likelihood, right? So because we only care about lambda, so just merge the terms related to lambda in both the prior and likelihood, right? So for the prior, the term related to lambda to some to the power of what, and correspondingly, the counterpart in the Gaussian likelihood will be here, right? So this is a lambda to the power of half, and this is a lambda to the power of a minus 1. So you merge them together, you get lambda to the power of half plus a minus 1, right? And then we merge the exponential term. So for both the prior and likelihood in the exponential term, the exponent is linear to lambda. So don't confuse the by x, right? It is projected to x, but it's linear to lambda. And now you just add them together, right? So it end up with minus lambda and b plus 1/2 x minus mu squared, right? So now what can we conclude? Look back to the prior form, right? if a density has the form of lambda to the power of something, and exponential to the power of a linear term of lambda, then that is a gamma distribution. That means, okay, this is a gamma distribution. No doubt, there's a gamma distribution, and then I can identify the parameters. So we have a mu A and mu B parameters for this posterior distribution, which is gamma as well, and A star is A plus 1 over 2, and B star is B plus half of the square of x minus mu. So this is the posterior distribution of the precision. Any question? Yeah, it's quite mechanical, but I still suggest you to follow this and to verify by hand. Then it will deepen your impression. Now let us extend this case like to the even more general situation. Like, so now suppose I want to know, I want to deal with a multivariate Gaussian distribution. Right? And now I want to place a prior over the precision matrix. So what is precision matrix?
Inverse of it.
Yeah, inverse of covariance matrix. Precision matrix is an inverse of covariance matrix. So now I place a prior over the inverse, over the precision matrix for some multivariate Gaussian distribution. So here's the called V-sharp prior. So V-sharp prior is also determined by two parameters. The first parameter is this positive definite matrix W. I should have the same size as lambda. So if this lambda is d by d, and W is d by d as well. And the nu, the second parameter nu, is a scalar, which is called degree of freedom. And we should ensure that nu is no less than b plus 1. And then the density will look like this. So the normalization constant is pretty complicated, but for now we don't need to memorize it. We only need to know the terms only relate to lambda, big lambda. So it turns out to have two terms as well. So the first term is determinant of lambda to the power of v subtracted by d by 1 over 2. And another term is exponential to the power of this minus half trace term. So you can see it's actually trace inverse of W multiplied with lambda. As we emphasized before, a trace is a generalized version of the inner product. So keep this in mind. It will ease a lot of your complications. Trace is a generalized inner product. So if you do the trace over two matrices like this, so first you can conclude that A and B must have exactly the same size. Otherwise, it's not a valid trace operation. And second, trace of A transpose B is equal to you first vectorize A and then vectorize B and calculate their inner product. So how do you vectorize the matrix? You can just concatenate all of these columns. You get a long vector, right? So if we calculate the trace of A transpose B, it is equivalent to you first, concatenate all the column vectors in A and all the column vectors in B, and then just calculate inner product of these two vectorized matrices. So then we'll go back, look at the density of V-sharp prior. So this is essentially an inner product, right, between your random variable lambda and the inverse of W. So it's essentially a linear term. Nothing complicated, it's just a linear term. So now suppose I use this feature are required to generate one sample of this d by d positive definite matrix lambda, right? And then I use this lambda as a precision matrix for some multivariate Gaussian distribution, parameterized by mean mu and covariance lambda inverse. And I generate a sample, d by 1 random vector x. So this is a density of the multivariate Gaussian distribution. I highly recommend you to memorize this because it's easy to memorize and it's used everywhere. Now we try to compute the posterior distribution of this big lambda given x. How can I do that? An idea? Yeah, follow exactly the same recipe, right? Just multiply the prior likelihood and see what can we get. So when we multiply them together, you will see if we just look into the terms related to big lambda, because all we care about is posterior distribution, right? It also contains two types of terms. One type of term is a determinant term to the power of something, right? And the second term is an exponential term. And for both likelihood and prior, the exponential term is linear to lambda. So don't confuse here. Y is linear to lambda. We mentioned before, right? So first, this is scalar, right? So that means I can put a trace operator on top of it. So this is probably I should over here. This is 1 half minus 1 half trace x minus mu transpose lambda x minus mu, right? This is scalar. You do the trace is itself. And now we can use the nice property of a trace operator. So remember, if you do the trace of a chain of the product, you can rotate the chain. You can actually rotate the chain. So it will be, you just move C to the front, so it will be trace CAB. It will be trace BCA. It will be trace CAB, whatever. So every time you just take one part on the right hand side and move them together to the left hand side. The result is exactly the same. I hope I can make you recall some basics in your work. Okay, so here we'll apply the trick here again, right? So I can move this vector. This vector is a matrix as well, right? I can move this to the front. So now it becomes trace x minus mu transpose and big lambda, right? So now we have this linear term for lambda. This is a matrix. This is the auto product of two auto product of the vector. Right? It's a matrix. It's d by d matrix times lambda, right? So now we merge this term with this term. So we end up with this. Right? W inverse plus x minus mu of x minus mu transpose and times lambda. Does it make sense? And then for the determinant term, it's pretty straightforward, right? You merge this and merge this, you end up with mu plus 1 minus d minus 1 over 2, right? So question, what is this distribution? It's V-sharp, right? But what are the parameters of this V-sharp distribution? What is the new degree of freedom? For the new degree of freedom is obvious, right? It's just the original degree of freedom plus 1, right?
Oh, yeah.
So the new degree of freedom is just original degree of freedom plus 1. And what about W? What about the W matrix? So the standard form, the trace term, you have to take the inverse over W, right? But right now, we have a summation. This is not inverse. Then what is new W? Yeah. Yeah, heard it, right? Just take the inverse over that. So you take inverse over that, you get the parameter, new parameter of the posterior, which is also the Gaussian distribution. So now comes the question. For a valid Gaussian distribution, you should ensure that your W is positive definite, right? But how do you ensure this point? How do you ensure this summation is positive definite? Is invertible. If it is not invertible, it's not valid, right? So the question is, first, is this summation invertible? Second, is this summation positive definite?
Two positive matrix is also a positive, right?
Yeah.
And you can prove that x minus a times x minus a transpose is also positive definite. It's easy to prove because
Yeah. I'm happy that everybody has recalled the actual stuff, right? So first, W is a positive definite, right? So this is a obvious about positive definite matrix. And this one, the auto product for arbitrary vector is positive semi-definite. It's not positive definite, it's positive semi-definite. But when you add it up to a positive definite matrix, it must be a positive definite matrix. And proof is straightforward, just apply the definition. Just apply definition, right? For arbitrary x. So for an arbitrary x, which is not zero vector, right? So if you take the quadratic form over that, so if we remove the inverse, right, you have a x transpose W inverse x plus. Sorry, let me put it bar at the bottom to differentiate x inside. So x bar transpose minus mu, x minus mu, transpose x bar, right? So the first term is positive definite, means that it is always positive, right? And second is non-negative. So positive term plus non-negative term is still a positive term, right? Does it make sense? Anyone feel confused? Huh?
So is that x transpose times W inverse times x? On the left? Okay.
This one?
To the left.
This?
Yeah.
Because W is positive definite, right? Its inverse must be positive definite. So what's the definition of positive definite? For arbitrary non-zero vector, this quadratic must be a positive number. Yeah. So then this must be positive, right? And this must be non-negative. This must be non-negative. Keep in mind, because this is positive semi-definite, there's such a difference, but this is non-negative. And then non-negative number plus a positive number always a positive number. Yeah, if you still feel uncomfortable, you can like open your book of the class, open a book, and look at the definition of positive definite and positive semi-definite. It's really not complicated, at least for this case. So now we can conclude that our posterior distribution for this precision is also a V-sharp distribution, and it is new parameters. The freedom, degree of freedom plus 1, and this W matrix is W inverse plus this auto product, and take the inverse again. So which prior is conjugate to multivariate Gaussian distribution. So those are commonly used conjugate prior distributions. So in the future, if you are required to design your probabilistic model, especially hierarchical Bayesian models, those are natural choices. Because it's so common that you use a Gaussian distribution to model some random variable, continuous random variables, right? And then you want to put some information, some prior information. You consider, oh, what kind of prior distribution I can add into my model, right? Gamma prior, right? Or Weishart prior. And on top of Weishart prior, what kind of other things I can do, right? Layer by layer, layer by layer. So, but you should know some criticisms about the conjugate priors. So, the invention or the discovery of the conjugate distributions is mainly for computational easiness. So, people always ask, in addition to this computational convenience, what else the conjugate prior can give you? So, is the conjugate prior the appropriate way to assign you the prior distribution? Right? It depends, right? Sometimes it might be probably, sometimes it might be not that reason. So it is likely that you have some kind of very good, very nice prior probabilities, but you cannot compute the corresponding posterior distribution. So be aware there is a criticism on that. So now we'll switch to another important concept called exponential family. So exponential family is a key, or is a cornerstone of the approximate inference or Bayesian inference. As we emphasize a lot, right? So Bayes rule, 99% chances won't work. You have to use some approximate computation to get the posterior distribution. So the common strategy is like this, right? I know this is the true posterior distribution, and it's so hard to get it. And now I want to find an approximation to this true posterior distribution. How should I do that? I should first find out a family of distribution, a family of easy distribution. And from this family, I want to find one which is best approximation to the true. And what kind of family of distributions are commonly used for approximation?
We don't have any idea of the true distribution. How do we compare the
No, you have an idea. Of course, you have an idea.
Oh, it's only that it's computational interaction.
Yeah, it's only computing trouble. In most cases, you do not know the posterior, but you know the joint probability. The major burden is that you cannot normalize it. Right? So of course, you have the information about the posterior, but you cannot get the exact form of posterior because of normalization. But anyway, we'll go to the detail later. But right now, I just want to give you a sense how the exponential family is introduced and used in approximate inference framework. So the basic idea is that I want to designate a family of easy distributions. It's easy, but it's kind of rich and flexible. And in this easy family, I want to find one which best approximates the true posterior distribution. And this family is usually chosen as exponential family. So the exponential family has very nice and easy form, but it is rich, and as you will see, many commonly used distributions belong to exponential family. So here's the definition of the distribution in exponential family. So suppose this is your random variable x, and in general, we just assume it's a vector, it's a random vector. And it's parameterized by this vector, eta. And eta is not necessary to have the same length as x. So be aware. It's not necessary to have the same length. And the general form or the standard form for an exponential family distribution will look like this. So first, we have some constant term to eta. So you can have any function of x as a constant to eta, but it must be non-negative. And usually we just assume each x is 1. But to increase the flexibility of the exponential family, you can choose arbitrary integrable function of hx as long as constant to eta. You can choose another distribution for x, but it's not controlled by eta. But in practice, usually we just set hx as 1. And then we have a vector where each element is function of the random variable x. We call it ux. Ux is called sufficient statistics. You can call it like vector function x. So ux actually summarizes the information contained in the sample x. That's why it's called sufficient statistics. And in this exponential term, we just calculate inner product between the sufficient statistics and the parameter vector eta. So essentially, it's a log linear term, right? And the length of eta has the same length of the sufficient statistics, but it's not necessary to have the same length of x. And finally, eta. So here I want to give an official name for the eta. Eta is called natural parameters. So why it is called natural parameters? Why it's just called parameters? I will mention later. And the final term we should be careful, we should pay attention to is the normalization factor. So of course, because I need to integrate the whole density function to be 1, right? So of course, there must be some normalizer of that. And normalizer only depends on natural parameter eta. It doesn't depend on x. Why? Why?
Because it's summing over the entire domain of x.
Yes, because it's the integral, integral over the entire domain of x to ensure that, okay, this is a valid density function. When we integrate on x, there's no effect on x. It only depends on eta. So this is also called partition function or normalizer function, but depends on natural parameter lambda, eta. So yeah, here's just to emphasize normalizer is a function of the natural parameters eta. So sometimes, I mean, in some books or papers, they like to put everything in an exponent. So we can move the normalizer in the exponent of this exponential term. Then you need to take logarithm, right? So this one, right? It is exponential to the logarithm of 1 over eta, right? And logarithm of inverse of the z eta is just minus logarithm of the z eta, right? So we merge the terms to get this. Right? So many books use this definition as well, and we call logarithm of z eta as log normalizer or log partition function. And you probably have seen some papers keep saying like log partition, log normalizer. Right? Just refer to this. So this is a general definition for the exponential family. Now let us look at how we convert a few commonly used distributions into the standard form of exponential family. So the first one is everyone's familiar with Bernoulli likelihood. Bernoulli distribution actually is an instance of exponential family distribution. So we know that, okay, the Bernoulli likelihood Bernoulli distribution will look like this, right? Mu to the x, 1 minus mu to the power of 1 minus x is the random variable, and parameter is mu. So obviously mu is not natural parameter. That's why we should differentiate mu and eta. So to arrange its form into the exponential family term, sorry. We can simply first take logarithm and then take the exp, right? So it is equal to logarithm and exp. Okay? It's always whole. And then you take logarithm over the density, you get x logarithm mu plus 1 minus x logarithm 1 minus mu, right? And now just merge terms regarding x, you get, okay, this is x, and this term is logarithm mu over 1 minus mu, just the subtraction of two log terms, and plus logarithm 1 minus mu. And if you move this term outside exponential, you get 1 minus mu exponential to this term. So you see, this term is linear to x, right? And then we can look at the standard form for the exponential family. So this is the exponential family, right? We have exp to the power of linear term to a natural parameter eta. And this is hx constant to eta, and this is normalization function of eta, right? This is our arranged form of Bernoulli distribution. So we can match right now. We can say, okay, we can construct the sufficient statistics right now. The sufficient statistics of x, just x itself. Okay? And eta is this, right? So eta is actually logarithm of mu over 1 minus mu. And hx is 1. And z eta is actually this. Z eta is 1 minus 1 over mu. Right?
So in this case, eta and mu are the same.
Yeah. So right now it's a scalar. It's a scalar. It's a scalar distribution.
Oh, yeah, it's very good.
Yeah. So now we see there is the relationship between the natural parameter eta and the original parameter mu. Right? So the original parameter mu actually characterizes the mean of your Bernoulli distribution, right? So we can call it as expectation parameter or mean parameter. So we can see why we call it natural parameter rather than parameter, because it can be represented by another type of parameter. It's called mean parameter. And there's a relationship between the natural parameters and the mean parameters. Actually, this relationship is very interesting. It's very important. So now we know that, okay, the eta is actually a function of natural parameters eta, right? But right now, when we arrange the terms, we only get, okay, z eta in terms of mu. So now we can solve eta in terms of, we can solve mu in terms of eta and then substitute for mu, then we finally can arrive at the function of eta in terms of eta. Right? So it turns out the normalizer is 1 plus exponential to eta. So I hope after class you can follow this and try to convert the distribution into the exponential family by yourself. And let's look at another case, the multivariate Gaussian distribution. It belongs to the exponential family as well. And so this is the standard form, and it's determined by mu and sigma. Right? Mu is the expectation, sigma is the covariance, right? But sigma can be considered expectation of what? Difference between the auto product, difference between the random variable and the mean, right? So in some sense, it's another expectation. So now if we manipulate the terms in the multivariate Gaussian distribution, and you'll end up with this. So first, in the exponential term, you just put all the terms that contain x together, and then you leave all the remaining terms outside. So now we have two terms which summarize the information x. One is x as transpose, the other is x.
Well, can you go over again how you think that?
Just expand this. Just expand this.
Oh, okay.
Yeah. Just expand this quadratic function. You end up with this like. And then we can construct the sufficient statistics here. I have a u1x and u2x. u1x is this minus half xx transpose, and u2x is x half. This is a sufficient statistics. So someone might get confused here because this one is a matrix, right? So this one is a matrix. But in general, we can always vectorize matrix. Right? So if you want to represent as matrix, you can put a vector operation of it. Now, it doesn't matter. Why? Because this is the trace term. The trace is the generalization of the inner product. So the trace of this u1x with sigma inverse is what? Is the inner product of the vectorized matrices for this one and this one, right? So it doesn't matter. So correspondingly, our natural parameters will be represented by sigma inverse here and sigma inverse mu here, right? These are natural parameters. And to be like extremely rigorous, you can put a vectorization operator over here. But this one, sigma inverse mu, is already vector. Does it make sense? And now, if you arrange terms in this way, and also define hx as 1, you can convert the form of the standard multivariate Gaussian distribution in the standard form of exponential family distribution. So this is a u1x. This is u. Oh, sorry. This is u2x. And combine them together, we get ux transpose theta. Is it clear? Someone looks good, someone feels uncomfortable. Uh-huh.
When we multiply them together, the first one would be a matrix.
Yeah.
While in there we have the trace of that matrix. That means it's good.
So first, from this step to this step, is it okay for everybody? It's just the expansion of this. Just you do the expansion. You merge the terms with respect merge the terms that contain x, and you leave the remaining terms, right? You get this two parts. And so our focus will be on this exponential term that only contains x, right? So now, this is a trace term. Is it okay for everybody? Right. So now I can define u1x is vectorization of this minus half x. X transpose. Does it make sense? And eta 1 to be a vectorized of this sigma inverse. Is it reasonable? And I can define U2x simply to be a x, right? And eta 2 to be a sigma inverse mu. This is a vector. And now, this exponent using this weak parameterization is equal to what? U1x transpose eta 1 plus U2x transpose eta 2. Does it make sense? As just mentioned, trace is a generalized version of inner product. So you really do not need to do the explicit vectorization. That's why I directly put this matrix here. I hope you won't confuse at this point. Does it make sense? And now we get our mapping to the natural parameters and the sufficient statistics, right? So the remaining thing is about the normalization factor, right? So all the terms that do not relate to x are put here, right? Looks like a Gaussian, but it's not Gaussian. Because the eta will be 1 minus this term. Right? So the eta, the normalizer is represented in terms of the original mu and sigma. The issue is that I want to express the normalizer in terms of eta. And remember, eta and the mu sigma, they have some mapping between them, right? So the mapping is here. Eta 1 is sigma inverse and eta 2 is sigma inverse mu. Right? Of course, to be recursive, you should put vectorization on top of that, right? But you can do it in your mind. It's not necessary to write it down. Right? So, and now you can manipulate the form of the z eta and to represent mu and the sigma in terms of eta. You finally end up with this form. So when you want to express your multivariate Gaussian distribution in another way, this is one choice. So from the Gaussian distribution or multivariate Gaussian distribution as well as the Bernoulli distribution, we see that a distribution oftentimes are represented by some mean parameters. See, a Gaussian distribution is characterized only by the mean and covariance, right? Covariance is kind of another expectation. But if you put it in an exponential family, they are parameterized by the so-called natural parameters. So there obviously a mapping between the mean parameters and natural parameters. Right? And there is some insightful connection between the mapping. This connection can be expressed in terms of feature information matrix, which we are not going to cover here. And if we have time, we'll talk about the directional inference. We'll discuss more, because feature information matrix exhibits some geometric properties of your distribution. And if you conduct some stochastic directional inference, you can use this geometric property to do the natural gradient descent will accelerate the speed of the convergence of your argument. But just have something in mind. There is some insightful connection between the natural parameters representation and the mean parameters representation. So a very important property for exponential family is regard to the gradient of log normalizer. So suppose I want to calculate the gradient for this log normalizer. Right? How can we do that? According to the chain rule, I need to first take the gradient of the log function. Right? You need to put the parameter of the log function in the denominator, and then you take the gradient over z eta, right? And according to the definition of z beta, it is integral of this hx and exponential linear term over the range of x. Right? So if we take the gradient over it, in many cases, you can put the gradient inside the integral. That means you can switch the order of integration and the derivative. In many cases, it's valid, but there are some special cases not valid. But in our case, I mean, in machine learning, this always we can always use this kind of property. So if you first take the gradient on the integram, what will be the gradient? What will be the gradient? So this is a gradient for eta, right? So hx is constant. You just leave it. You just leave it outside. So you multiply with hx, which is constant to eta, and then you take the gradient over this exponential term. We need to first replicate this exponential term, right? And then according to the chain rule, you take the gradient to the exponent. What's the gradient for this term? It's just ux, right? It's just a sufficient statistics. Right? And then you take the integral outside. That's the gradient for this normalizer. Now let's put together, right? Let's combine this and this and say what can we get. So this is a gradient of the normalizer, and because you take the gradient for the log normalizer, you should divide this gradient over z beta. Right? So it will be if you put this a beta inside the integral, because it's constant to x, right? And you just copy this one here. So what is the integral? What is this part?
So that cancels out.
This is density. This is density of the exponential family distribution, right? It's p of x given eta. Question?
No, I was checking, but it doesn't practice.
Yeah, I can. Yeah. This topping, right? The same here in the integral. And multiplying with this ux. So it's actually the expectation of your sufficient statistics. Okay. Yeah, that's a very useful problem and a very famous conclusion. So that means if you take the gradient over the log normalizer with respect to the natural parameter, you're equal to calculate the expectation of your sufficient statistics. Very important property for the exponential family. And we will review this property when we look at some when we study the approximate inference again. This is a foundation for message passing algorithms. So some more interesting property. If you take the gradient over the gradient again, you get the second derivative of the log normalizer. It turns out it becomes the variance of your sufficient statistics. If your sufficient statistics is a vector, then it is covariance matrix. And again, this is a good practice to practice your matrix derivative. So I highly recommend you to do this, or probably I will consider to put it in the homework. Right? So now let us look at suppose I have like n observations, IID observations, x1 to xn. They are sampled from the same exponential family distribution. I want to get the maximum likelihood estimation of the natural parameters and see what kind of results can we get, right? So if you write down the joint probability, you just multiply the likelihood for each data point, it will end up with this. Because they eta are shared by all the data samples, so you have the eta to the power of n in the denominator, and in numerator, because each term is exponential linear to eta, right? So it just adds them together. So it's simply multiplication. And now, so we take logarithm over this joint probability, and you get this, right? And now we take gradient and set gradient to 0. And say if we solve this gradient p0, we get that we'll arrive at it here. The gradient of log normalizer is the average of the sufficient statistics over all the samples. So, I mean, if you want to get optimal exponential distribution, I mean, in terms of maximal likelihood estimation, right? So the right-hand side is known as the empirical mean, right? Empirical mean of your sufficient statistics. Right? And left-hand side, what does it mean? What's the left-hand side? Yeah, that is the true mean, right? Expectation of UX. So basically, it says that if you want to find out a MLE estimation for your exponential family, you essentially just set the empirical mean of the sufficient statistics as the true mean of your distribution. That's it. So there's another interesting observation from the exponential family. You can say, okay, they're elegant, nice properties, right? Any questions so far?
First, the probability distribution. That's just the definition of maximum likelihood estimation, right? The P of D given.
Yeah, it's just this. If you substitute this is just the P x I x n given eta, right? If you substitute for this likelihood with the exponential form, you will immediately end up with this. So you can do this. You can do this tedious work by yourself. I didn't do that. This making slides. You have to type a lot of such kind of long formulas. So I think it's so straightforward. I just put the results. Does it make sense? So this is the empirical mean, and this is the true mean. And you need to set the empirical mean to the true mean to get the MLE estimation. So what's the conjugate prior to the exponential family likelihood? So this is a general form of the conjugate prior to exponential family likelihood. So the conjugate prior is parameterized by two parameters. One is chi, and the other is mu. It's also called degree of freedom. And then you can see that it is proportional to the normalizer to the power of mu. So the normalizer is the normalizer for the likelihood. So you can see the connection between the prior and the likelihood. You must have some connection. You cannot put arbitrary term in your prior distribution. That won't guarantee the conjugacy. And then exponential term to the power of mu, this is also a linear term. Eta transpose times the chi is vector. So if you now multiply the prior and the likelihood to capture the posterior distribution, you'll end up the form like this. So first, in the prior, it is z eta to the power of mu, and this is z eta. So it's z eta to the power of the mu plus 1, right? And for the exponential term, you just merge the exponent, so eta transpose mu chi plus ux. So you can see this form, the posterior of this form, has the same form as the product, right? So this is a conjugate. It's a conjugate product distribution, and it's parameterized by nu plus 1, and this summation over nu plus 1. Why? Because the exponential, in the exponential term, you have to do the inner product between eta and nu pi, right? That's why you have to divide this summation over nu plus 1 to make the form to be consistent. Is it clear? I think this is pretty straightforward, and it's hard to like just use I to derive this. And anyway, not everyone is like von Neumann, right? So just give you a sense, and I highly recommend you guys to do this yourself. Use your hand and paper, and you will see how the posterior and prior match. And mu here can be explained as a pseudo count, right? You can consider in a prior domain, like you have some pseudo observations nu times, and then after you observe some observations, which is expressed as the sufficient statistic over the observation, you have this weighted summation of observation. So nu over nu plus 1 high from the prior, and this fractional represents the part from the observation, and the total pseudo count now increased by 1. So actually you can match this to all the conjugate prior and likelihood cases we just mentioned. Beta, Bernoulli, Dirichlet, categorical, and gamma, Gaussian, V-sharp, multivariate Gaussian. There's all special cases for this. And interestingly, this also belongs to exponential family. If you take a look, it also belongs to exponential family. And I will leave as an exercise for you to verify. And it will say these two exponential family distributions are conjugate if and only if one of the sufficient statistics are shared as the natural parameters in another distribution. You will see the connection between the prior and the likelihood. You must have some links, otherwise there won't be any conjugacy. So I have introduced those important concepts, and just a few things you need to know. First, what are conjugate priors? What's the motivation? And what are commonly used conjugate priors to commonly used likelihoods? Definition of exponential family, how to turn the existing distributions into the standard form of the exponential family, properties of exponential family, and the general conjugate priors to the exponential family. Those are very, very important. I spent quite a long time because at the beginning I thought it's so easy, so standard, so easy. I didn't spend time to really understand the exponential family. And turns out that later I waste a lot of time in understanding those, especially approximate inference algorithms. So this is really important. Okay, so again, we'll postpone the homework 0 to next Monday, and hopefully everybody will finish it by that time. And we'll very probably release our second homework, homework 1, on Friday. And feel free to come to the office. I will ask questions in Canvas or send emails. Okay, I'll see you